and welcome to another astronomy lecture. This time we're talking about black holes, and in order to do that we're going to need to talk first a bit about space-time and how it occurs. This is from chapter 24 in the text, so this is just the first part of that chapter, but again, if you're not reading in the text, then this is just going to be a lecture pretty much about space-time. We're going to first talk about space-time a bit, and then I think the next lecture actually get into thinking about black holes as a consequence of space-time being curved. Okay. So here we have an image. On the left is optical, meaning like visible light. This is a region in the constellation Cygnus where we're pretty sure there is a black hole that is part of a binary system, and it is sort of devouring its binary companion. On the right is an illustration or interpretation of what it might look like if you were close enough to see this pair of black hole and star. The other star in the system, we believe, is a giant star. It's a big star. I think it's an O-class. We'll get to more of this later, but in this image you can kind of get an idea that the black hole is sort of spinning around and pulling in material from the other star. And since it's spinning, just like when stars were forming, you end up creating this disk sort of around the black hole that's sort of in the plane that the black hole is spinning. And then also, when something's spinning like that, you can end up ejecting material or creating sort of beams of energy that come out of the poles of this object. But we'll get back to more of this later on. So a quick recap. Most of the stars end up as white dwarfs or neutron stars. In fact, the majority of them will end up as white dwarfs, right? Because most stars are low mass stars. We also looked at some region of high mass stars, which were stars that during their lifetime were greater than about 8 times the mass of our sun. So if you were greater than 8 times the mass of our sun, but less than about 10 times the mass of our sun, a star would end up as a neutron star. And these objects, white dwarfs, neutron stars, these are the cores left after the star has ended its fusion lifetime. It can't fuse anything else, so it either pushes off its outer layers or blows them off, depending on the kind of the size of it overall. So what's left is that core, and if that core is less than about 1.4 times the mass of our sun, that's going to kind of end its life as a white dwarf. And this is when the collapsing of that core due to the force of gravity crushing things in is not terribly large, and so it's able to be stopped by what I told you about was this electron degeneracy pressure, which is basically electrons not wanting to overlap in the same space, be in the exact same place, so they push back when they get too close. In terms of the core, it turns out that if you're greater than about 1.4 times the mass of the sun, but less than about 3 times the mass of our sun, right? We're talking about the stellar cores now. Those are the things that ended up as neutron stars. And in that case, there's enough mass that gravity could overcome the electron degeneracy pressure and eventually get to this point where you crush everything, sort of becomes neutrons, and then you get to the point where the neutrons start to overlap and they have their own degeneracy pressure, right? They don't want to overlap, and so they push back, and it's much stronger than the electron degeneracy pressure. So that's what we've talked about already. The new thing now is what happens when the core that's left over after a star has finished its sort of normal lifetime is greater than about 3 times the mass of our sun. So it turns out that if you're larger than this, then the gravitational collapse, that crush due to gravity, even overcomes the neutron degeneracy pressure. And at that point, there's nothing that can stop gravity from just collapsing without end. This produces an object that we now call and understand and think about as a black hole. Just to note that black doesn't necessarily mean that you can't see these objects ever. The objects themselves may be difficult to see, but as it turns out, black holes are part of what creates some of the most energetic and brightest events in our universe. Even like in the last slide, when the black hole was eating up a companion star, then it's actually generating quite a lot of light. So we're going to think a good bit about something called relativity and particularly general relativity, which is the current leading and best theory of what gravity is and why massive objects tend to pull on each other. So before we get too far into that, I wanted to say something about why it is we even need this thing called general relativity. So you probably know that for a long time our understanding of gravity, the leading best theory of gravity, was one that Newton proposed, formulated, hundreds of years ago, 1600s or something like that. And it remained the best theory for hundreds of years, partly because it worked very well. And in fact, it still works really well in most of our normal situations, right? Normal day-to-day situations, we're living on Earth, gravity's not too strong. Newtonian gravity, as we call it, works very well. You can use it to send rockets to space, to orbit around other planets. So what's wrong? Well, I tried to think of a good way of explaining this difficult thing, but basically, Newtonian gravity is a very good description, like I said, in the normal situation we're in. But if you look beyond our normal situation, in places where gravity is much, much stronger than it is here, Newton's description doesn't work so well anymore. So the sort of analogy that I came up with is like, if you look at a tabletop, right? You're looking at a table and it looks smooth. It's flat, smooth. And for most purposes, for normal purposes, saying the tabletop is smooth, perfectly good description, right? However, this is only because we're using just our eyes to look at it. If we were to look closer or examine more closely using something like a microscope, right? We look at the tabletop, it turns out it doesn't look that smooth anymore, right? It's got all these sort of bumps and jagged peaks and all this different wild sort of terrain. It's not smooth anymore. So if you ask yourself, like, which of those descriptions is correct, is the tabletop smooth or is it not smooth? Well, they're actually both correct in their own way, right? They just apply at different levels of scrutiny, right? Like, how closely am I examining this thing? So if you were to start at the microscopic scale, somehow able to look very, very closely and see the actual really rough surface on that very small scale of this tabletop, and sort of zoom out, then that roughness is going to slowly smooth out, right? You're going to back up enough where you can't see that stuff as much anymore, and it looks smoother and smoother and smoother, until eventually you zoom out to like your normal vision, it looks entirely smooth again. So in that analogy, looking at this tabletop with our eyes is sort of like Newton's description of the tabletop. It is still correct in its way when you are only concerned with looking at it at this level, but if you're interested in sort of getting closer or looking in more detail, turns out it's not so good anymore. Still though, as you transition from one view to the other view, it makes total sense. Right? If I back out from that microscopic view, eventually I come to a view that looks just like I would expect it to with my eyes. This whole thought process has something to do with what's known as the Correspondence Principle, which is sort of requirement that any new theory still returns us the original or the sort of old results that we know are correct. So since Newton's theory of gravity works just fine in our normal circumstances, our new theory, general relativity, still better give us the same results that Newton did in our normal circumstances, and it does. So in normal circumstances, general relativity gives the same results and predictions that Newtonian gravity does. But when you go into areas where the gravitational fields are extremely strong, general relativity starts to tell us different things than Newton would. Okay, so in order to get to understanding at least a little bit of the difference between Newtonian gravity and general relativity, we're going to walk through similar sort of thought process that Einstein was going through when trying to work out this theory of general relativity. And oddly enough, it had to do with thinking about something fairly simple, which is standing in an elevator and thinking about what's going on when that elevator is moving up, moving down, stationary, or if it drops. When the elevator's not moving, on the left there, you feel just your normal weight. if the elevator starts descending, starts accelerating downwards, then you start to feel like a little bit lighter for a moment. If you've ever been in an elevator, you probably have, you know this feeling, right? When the elevator starts to drop down for an instant, your whole body feels a little bit lighter. And the opposite thing happens when the elevator starts to go up, right? Accelerates upward, right? When it starts to move upward, for a moment, you feel heavier, right? Like you're pressed into the floor. And finally, if somehow the elevator were to fail entirely and just start dropping, then you don't feel any weight at all. You're no longer pressed against the floor at all. And in that final situation, keep in mind that when you're in this enclosed space, right, there's air all around you, but the air is all dropping along with you too, right? So you're all dropping straight down, so that means you're not running into any air. You don't feel any air resistance even. So you're entirely weightless. This final situation then is what we call a state of free fall. You're falling freely. And Einstein's sort of stroke of genius then was to connect these different scenarios with the fact that we're all imagining all of these in a gravitational field, right? Like particularly on Earth. These are all situations you're imagining on Earth. Kind of just naturally do that because that's where we live. However, if you're in these enclosed spaces, then you don't necessarily know what's happening around you. And like in the last scenario, when you're in free fall, there's no way to actually tell whether you're freely falling in this gravitational field on Earth, or if you were just floating in this box out in space somewhere. In that case, there's just no gravitational forces acting on you, so there's nothing to pull you to the ground, pull you to any side, just floating freely. Similarly, on the far left, we're in a gravitational field, we're being pulled down by gravity. But again, if you're in this enclosed space, there's no real way to tell whether you're actually in Earth's gravitational field or if that box was accelerating through empty space. You just put some rockets on the bottom of that elevator box and send it out into space somewhere and hit the thrusters and start accelerating, you would feel exactly like you were just standing in an elevator on Earth. It was sort of getting at the connection between an object accelerating and an object being in a gravitational field. Right? There's a very sort of deep connection between those things. Probably before we were sending people into space, it was harder to imagine this sort of state of free fall. Because most of the time, if you're in a state of free fall, you're probably falling towards the ground and not really worried much about how that state of free fall relates to just being in outer space, floating far away from everything. Okay. However, now we regularly have people orbiting the Earth, and that state of motion is technically a state of free fall. The image on the left there is some astronauts in the International Space Station, and they all seem to be floating freely. You've probably seen videos of astronauts floating around in ISS or in other spacecrafts. So I remind you that in order to orbit the Earth, an object needs to be moving at least, I think it was like 8 kilometers per second. So way back when I told you about orbits, I showed you this picture where you think about throwing something horizontally on Earth, and the faster you throw it, the further it goes, right? So you throw it pretty fast, that's like the A, it goes far but it drops, right? You throw it a lot faster, like in B, it goes really far but it still eventually drops into the ground. You throw it really fast, you throw it fast enough, 8 kilometers per second, then it's going so fast that as it drops, the curvature of the Earth is dropping as well, or the surface of the Earth is dropping because it's curved. So it's sort of dropping towards the Earth, but it keeps missing the Earth. So these people and the space station itself are continually dropping towards the Earth, right? So they're in a constant state of free fall. To be clear though, this is not a scenario where you'd say that they're like far away from any object, in empty space and not experiencing any gravitational pull. They are for sure experiencing gravity because that's what's keeping them orbiting around the Earth. Okay, so taking this thought process a bit further, where we're saying there's no real difference between being in a state of free fall or being just very far away from any object in space, floating freely. Technically, you would say being like far enough away from any object where you don't feel any gravitational pull from those objects. So think about then two people that are going to jump and be in that state of free fall and toss this ball back and forth between each other. Weird scenario to think of, but whatever. It's an imaginary thing. There's this bottomless pit, and they're just going to keep falling forever and ever and ever. And also, somehow, they're not experiencing any air resistance as they fall either. If you're going to imagine they're not. So what does this situation look like? Well, they jump off, one of them's holding the ball, and they're in that state of free fall, so they're just kind of like floating there, the ball along with them. And from their perspective, neither of them are moving relative to each other. I just look across and I see this person still constantly at the same distance away from me. And so when one of them throws the ball at the other, there's no need to like arc the ball. They just throw it straight, push it straight at the other person. From their perspective, it moves straight from them to the other person, and the other person catches it. Then continue along. The second person then just pushes the ball back at them, right? Again, just pushes it straight, because relative to the two people in the ball, none of them are moving. The second person just pushes the ball back at the first person. From their perspective, it goes from that second person straight to the first person. Right? They catch it. All well and good. However, if we think about what this situation looks like from an outside perspective, that would be like the black lines in this scenario. So as the first person pushes the ball to the second person, the first person, the second person, and the ball are all falling from this outside perspective. Me watching this all happen, terribly afraid for them, falling forever. But anyway, when that first person pushes the ball, it's falling. So what I would see is the ball doing this sort of curved path. It goes down as it gets to the other person. The other person catches it. Then the second person pushes the ball back, but from my perspective, right, everything's falling. So that ball also falls, which is this little arc. And remember that these people, we're imagining them in the state of free fall in a gravitational field, in Earth's gravitational field. But as I said earlier, if you can't really see outside this situation, then there's no way to tell whether this state of free fall is happening in Earth's gravitational field, or whether these people are just floating freely in space far away from any gravitational field. And we're not going to dig at it too much more, but that thought that there's no way of distinguishing between this state of free fall or floating in empty space somewhere, along with the fact that the path of objects seems to curve in gravitational fields, this also implies that if you were in a box that is accelerating through empty space and you threw an object, then watching that box from the outside, you would see the path of that object curve. What makes this all kind of strange in the end is that Einstein's equivalence principle applies to everything in space and time. That means it also applies to light, which is to say that if you shine a light in this accelerating box, right, in this rocket that's shooting through space, from an outside perspective, that light appears to follow this curved path. And so, in a gravitational field, the same thing has to happen, because these scenarios are indistinguishable. They are equivalent. That's where the name of the principle comes from. These scenarios are equivalent. In that accelerating rocket versus in this gravitational field, what's going to happen is indistinguishable. The light bends in the accelerating rocket, light also bends in Earth's gravitational field, and in gravitational fields in general. And just to be clear, the amount of the light bending is greatly exaggerated here. In general, gravitational fields need to be much, much stronger than Earth's in order for us to get any sort of significant bending of light, like you would see here. And so to understand, or to sort of explain why it is that light bends in gravitational fields, it's tricky, right? Because our idea of gravity before general relativity was that it was something that is created by massive objects. It's due to the presence of massive objects like me, the Earth, the Sun, and it acts on other massive objects. Earth and me, Earth and the Sun, right? These are massive objects, things that are made up of matter, have mass, pulling on each other. Light is massless. There's no mass to light. So why would it be affected by a gravitational field? In the sort of standard picture or thought of light, light's not affected by gravity, and so wherever it gets generated, it just zooms straight out. unless it runs into, some atoms and gets absorbed and emitted. That different stuff can happen, but it's not the mass of objects that you would think of as pulling on the light. So then sort of like the big leap for Einstein then was to say that, well, maybe light still travels in straight lines. It's just that mass actually curves the space that light is traveling through. And so what seems like a curved path is actually still a straight path, but through a curved space, which is a difficult thing to think about. So I have this example. I think it's a fairly nice way to illustrate this, where, I already said all this. So if you're thinking about something going straight, right, it doesn't change its direction. Well, the sort of straight path is usually like, be the shortest distance between 2 points. But if the space that that path is in is curved, then saying that it's straight can be a little bit confusing, right? Because if the space is curved, then there's not really a straight path anymore. There's a path that doesn't alter its direction as it goes forward, right? That's what we can consider straight. And in that space, that will still be the shortest path between 2 places, the shortest distance between the beginning and the end. So you can think about this like straight path or shortest path in a curved space by thinking about moving between places on the surface of the Earth. If we were to imagine taking a flight, say from Philadelphia to Beijing, if I thought that the Earth's surface is flat and just draw it out, and I get a picture of something like that on the left, and it would seem to me that the shortest distance, the straightest path from Philadelphia to Beijing, is just straight east to west, straight across the Pacific. And if I were to see on this flat version of the Earth that an airplane instead actually goes up through Canada, over Alaska, and then down through Russia and into China finally, it would be a little bit confusing. That path certainly doesn't seem straight, and it doesn't look like it's the shortest path. However, if we realize that the Earth is a globe, sphere, and we look at the sphere and draw that path on the sphere, it turns out it is a straight path, a path that doesn't alter its direction as it moves, versus the one that went through the Pacific, right, is constantly sort of turning. In fact, the path over sort of Canada and Alaska is about 3,300 kilometers shorter than the one that would go through the Pacific Ocean. So thinking about light curving or appearing to curve in gravitational fields, Einstein said, well, what that really is light going in a straight path, but through a space that has been curved. The space itself is actually curved or warped. Another sort of analogy to understand a bit better what it means to move in sort of a straight path through a curved space. So for this analogy, we're going to think about having an ant, and you somehow train this ant to walk only in straight paths, right? Meaning, 1 foot in front of the other. It doesn't alter its direction as it moves at all. So you have that ant, and we're going to put it on this sort of rubber sheet. So this sheet has been stretched across these 4 posts, and nice and taut, right? Just the ant on there. It's a pretty much flat surface. So if we were to set our ant down there, let it go, it's going to walk straight across. It doesn't alter its path. From his perspective, it's going straight. For outside perspective looking in, it seems like it goes straight too, right? The space is flat. However, if we start placing objects on this sheet, larger and larger objects, that's going to start stretching or curving the sheet more and more. And even though the ant is going to continue walking its straight path whenever we put it on there, from our perspective or from outside of that sheet, the ant seems to follow a curved path. So you can imagine placing like a pretty small object on the sheet, right? Like a grain of sand. This being really small, very little mass, then there's very little stretching it's going to do to this sheet, right? Almost imperceptible. So if you put the ant and have it walk across, it pretty much seems like it's still going in a straight path. So this is like an object that's not very massive, so it doesn't have a very strong gravitational field. It's not stretching or warping the space around it very much. If we put a bit bigger mass on there, right? Think about taking the sand grain off, put a pebble on there. Pebble, a little bit more massive, still not a whole lot of mass, so it will stretch that sheet a little bit more, but not a whole lot, right? And we have to probably even kind of look closely to see that the sheet does look stretched, and also that if we put our ant on there and it walks along, if we don't look closely, it could still look like the ant's going straight. But you kind of look a little closer, and you can see that the ant's path might deviate a little bit, or it looks like it curves down a little bit as it goes by the pebble. Finally, if we think about putting like a heavy object on that rubber sheet, like a heavy solid paperweight, then it's going to stretch that sheet quite a bit. It's going to warp or curve that sheet quite a bit. So in that case, we now get a picture, something like this, right? Where we put a heavy object on the sheet, it has stretched the sheet down quite a bit, and if we set our ant on the sheet to walk across, when it gets anywhere near where that paperweight is, its path will seem to curve quite a lot, right? It curves all the way down there, comes all the way back up and keeps going. But again, from the ant's perspective, it's not changing its path, or it's not changing its direction, it's going straight. From our outside perspective, it certainly seems to curve. And that is because the space that it's in is curved. So if we do connect these analogies to actual objects, or more useful objects, this paperweight would be something like a white dwarf or a neutron star. This is something that warps space pretty significantly. The sand grain then didn't really do much of anything. It's actually kind of like Earth. Right? Earth is pretty big, but in terms of warping space-time, it doesn't really do all that much. This is why, for a long time, we never noticed it. Okay? Didn't look all that close. The pebble then, kind of like the sun, does a little bit of stretching, but still not a whole lot. So hopefully you're getting the idea that very massive objects will warp space-time more, but it turns out that it's not just how massive the object is, also how compact that object is very important. So a white dwarf does a lot more warping than the sun, even though a white dwarf could be a similar mass, like one solar mass. White dwarf is going to do a lot more warping than the sun, even though they could be about the same mass. And this sort of makes sense when you think about placing objects on this sheet, right? Because if I were to have this paperweight, but I smush it down, right, and I spread out that weight, then when I place it on the rubber sheet, it's not going to stretch the sheet down as much, because that mass is spread out a bit more, and so it doesn't exert quite as much downward pressure on the sheet. And so the sheet is stretched, but not as much. Versus you concentrate all that mass together and put it on that rubber sheet, it's all acting in this very concentrated area, and so it stretches a lot more. So yeah, not just how much mass, but also how compact that mass is will determine how much it stretches space-time. So that's all thinking about like light going in straight paths, but appears to curve because it's moving in this curved space. General relativity, though, is a theory about gravity in general, or explains the force of gravity, or the effects that we see as gravity, by describing space-time as curved. And it's curved by mass, which means it's something like a planet orbiting a star, even though Newtonian gravity can describe that situation fairly well with the forces pulling between the star and the planet. We can also now understand that the more fundamental picture is that the star is warping the space around it, and the planet is sort of following this kind of stable path in that curved space. We have this little video to hopefully give you kind of a better understanding of like an object moving in like a flat space, right? Like a planet just kind of rolling through space, and it just looks like it goes straight from its perspective. From any other perspective, it's just looking like it's going straight. But if you put a large mass in that same kind of region of space, then that space is curved, and the planet then will start to take this sort of curved path, this circular or elliptical path. You got a flat sort of space-time there, roll the planet along, and its path pretty much straight. You got this nice view from above. Now, take a big object, right, like a star, put it in that space-time. It's now warping space around it, curving the space around it, And if you move a planet through it, then it starts to just naturally wants to move in these sort of elliptical paths. So there you go, like he set it in motion there, and instead of just continue to go roll along, it comes back and moves around in this elliptical orbit. This being a rather small situation, and there being friction between the ball and the actual fabric that we're saying space-time, it doesn't actually last all that long, this orbit. However, when you get to very, very large scenarios, the Earth's moving very, very fast, it's not losing any energy to friction, that motion in the curved space-time is very stable. It continues to orbit around a long, long time. Part of what it was also showing in the overview is that even when the star was there and the whole space was stretched down, if you're looking down on the top, right, you're sort of seeing this outside perspective. You can't even really tell that the space is warped, right? The grid still looks like the grid. It looks straight down. Part of that is that this warping is in, like, fourth dimension in a way, something that we have a very hard time perceiving. It's also the case that we are very small in the sort of scale of warp space-time. And so we are kind of like the ants in that stretched sheet scenario. We're so small that even when we move along this space and it curves, we're not really going to tell. So the next thing we're going to do is look at ways that this idea, this theory of general relativity was tested. And kept passing all these tests and still passing any test that's been thrown at to this day. It's correct. As far as it goes, maybe we're going to look closer again at some point and get a theory that explains even stranger things, right? But for things that it explains them very. Before we get to that though, just wanted to do a quick side note to try to emphasize how Newtonian gravity and what we would call a classical picture of space and time is fundamentally different from this picture we have now in general relativity of a sort of interconnected space-time. In the classical view, basically space and time are just always what they are. Space is unchanging, it's absolute, always the same. Time always flows at a constant rate. It ticks away 1 second, 2 seconds, 3 seconds, everywhere throughout space regardless. Right? Time is just consistently flowing. And there's some quotes from Newton, I think in his Principia or something, where he was describing his theory of gravity. Right? He talks about absolute true mathematical time of itself and from its own nature flows equally, without regard to anything external. Right? Say that time is just this consistently flowing thing. Right? It moves along, doesn't care about anything else. And on space, it says absolute space in its own nature without regard to anything external remains always similar and immovable. Again, saying his idea of space is just unchanging. And Newton wasn't the first person to come up with this, right? These are ideas that go back at least to like ancient Greek times. People like Aristotle and Euclid had similar ideas about space and time. And beyond that, these ideas are fundamental and deeply embedded in Western thought at least. As I said, space is not absolute. Space stretches. And space and time are part of the same fabric of the universe. And so if space stretches, time also stretches too. So when we go to this modern view of space-time, we end up having to give up some sort of central beliefs that we had in our old view of space and time. And some of those things are like the size of objects being the same. Like if I have a basketball, you might think that that ball is always going to be the size that it is. Doesn't matter where it is, doesn't matter how it's moving. It's just the ball, right? It's going to be the ball. Turns out, no, sorry. It can shrink, right? Depending on the situation, it can be stretched, right? Depending on the space that it's in. That's just how it is. Something else is like durations of time. So like how long something takes to happen. Remember, space and time are part of the same thing. And space stretches, time stretches. So when you say how long something took, it can depend on your perspective of that series of events. And finally, even the ordering of events, like which thing happens first. You have like event A and event B, and which of them you say happened first actually depends on your perspective when you're looking at them and the space that they're in. Their ordering is not set. So in this modern view of space-time, these things that we think are just constant, like size and times and orders of events, they're just not constant anymore. It's just how it is. Even though that's true, I should say that these sorts of changes, where like the size of an object changes depending on like how fast it's moving, don't happen in our normal scenario, right? Our day-to-day on the surface of the Earth, not moving too fast, not a very strong gravitational field, right? This is normal. So the stuff that we experience in our day-to-day lives pretty much all goes along very nicely with the classical view of space and time. It just turns out that when you look closer, a more sort of fundamental picture of space and time and the universe, it doesn't keep to that like absolute space and evenly flowing time. Those things are changeable. Hopefully you get by now that general relativity is sort of the next stage of our understanding of gravity. We had Newtonian gravity for a long time, it worked really well, but now that we can like look into areas of the universe and think about areas of the universe where gravity gets really, really strong, it doesn't work so well anymore there, right? We need general relativity. Why do we accept that general relativity is correct? Well, there are many reasons, and I'm going to tell you about a couple of them. One of them has to do with the orbit of Mercury around the Sun. Before we talk about Mercury, though, you should know that all the planets are orbiting around the Sun in these elliptical orbits. We talked about this a lot more in the beginning of the course, where the shape of the orbits for all the planets is actually pretty close to being a circle, but none of them is exactly a circle. They're all squished a little bit. Okay? So they're all what we call elliptical. What that means, and it's shown in this sort of picture here, very exaggerated in this picture, is that at some point in the year the Earth is a bit closer to the Sun, and at sort of like the 6 months from then, the Earth will be a bit farther from the Sun. So if we think about just the original orbit that's shown here in the animation, right, at one point the Earth is really close to the Sun, or closer to the Sun, and then 6 months later it's all the way on the other side of the orbit, and it's further away from the Sun. Again, our orbit is really quite circular, so the difference between being closer to the Sun and further to the Sun is not nearly as what's shown here, right? It's not as big of a difference as is indicated in this animation. It's sort of exaggerated, so you get the idea. Right, so we're all orbiting in these ellipses, and something else that happens is that where the ellipse is, or the ellipse's orientation, tends to advance over time, which means that the closest point that the Earth comes to the Sun, or any of the planets comes to the Sun, is going to change over time. At first in this animation, it's like right there on the left side, right? But a little bit later, that whole orbit has sort of advanced or rotated around, and now the closest point to the Sun is actually like further down, towards the bottom of that orbit. Now the movement of this whole orbit around is what we call orbital precession. It's precession of this orbit over time. Using just Newtonian gravity, we can pretty much explain the precession of Earth's orbit just by considering the fact that like Jupiter and Mars and Venus are also pulling on Earth a little bit, and so overall the orbit doesn't stay stable, it kind of advances over time like that. So that's most of the planets though. It turns out that Mercury's orbit is not as easily explained by just thinking about its precession being due to the pull from the other planets. So Mercury is the nearest planet to the Sun, meaning it experiences the strongest gravitational field in the solar system. Right? The Sun is the strongest gravitational field around, and Mercury is closest to it. So it's in the strongest gravitational field, which means it's also experiencing sort of like the most stretched or warped space-time in our solar system. So its orbit also precesses, or sort of advances over time, and Newtonian gravity, if you calculate how much it should advance due to just the pull of the other planets, then you get some value, but it's too small. Right? It's not enough, because we can compare that to Mercury's actual precession, and as long ago as 1850, in the 1850s, it was pretty clear that Mercury's orbit was precessing faster than we could explain with just Newtonian gravity. So one of the first things that Einstein did was calculate what you would expect the precession of this orbit to be due to this new understanding of warp spacetime. And it turned out to be pretty much exactly the right amount that was missing from Newtonian gravity. Right? So with Newtonian gravity, you could calculate this precession, and it turned out to be, well, they usually measure in arc seconds per century. It's a very slow advance. 531 arc seconds per century for 100 years, which means that the orbit will have rotated all the way around and come back to where it started in about 678 years. A long time. However, the measured one was about 43 arc seconds faster than that. So the measured one is about 574 arc seconds per century, meaning that Mercury's whole orbit will advance all the way around the sun and be back to where it started in about 627 years. So like 50 years faster than would have predicted just with Newton's gravity. And using general relativity, Einstein could explain exactly this kind of difference or missing 43 arc seconds. So that was a really nice sort of check on general relativity, but probably the most famous check that happened, at least in Einstein's lifetime, was something that he used his new theory of general relativity to predict what you would see when you look at stars that are very close to the sun. And people hadn't really done that before, or people hadn't really thought to do this kind of experiment before. So when they went and did the experiment, after he had told them what to look for, they found it. That's exactly what they saw, right? That was big sort of confirmation that general relativity was giving the correct description. So this is that other test. As I told you, when light moves through a strong gravitational field, right, where the space is stretched significantly, then its path appears to bend. So in this diagram up here, you think about like there's the Earth over there, here's the sun, and there's some stars that are way far off to this side here. Right? So far off that their light all comes in pretty much straight at the sun. So if the sun weren't there, then the light would have come just straight from this star, passed right through because the sun's not there, and go straight to Earth. And we would see the star, straight across here. However, when the sun is there, the light that would have gone straight gets blocked, so we don't see that. But there's light that comes just around the edge of the sun, and it curves as it goes by the sun. So it curves down, deflects a bit, and now comes towards Earth. When we look at that from Earth, though, we don't see the curvature of space. We just see a light ray coming to us, and so we look back and we kind of project back and say, oh, that star is actually up here, instead of where it is down here. So this only happens when stars are really close, or their light passes really close to the edge of the sun. So what you can do is just look at a group of stars normally, and then look at those stars, that group of stars, when they come near the sun. And you can see relatively like the positions of those stars. The ones that are closer to the sun will sort of move away a little bit. They seem like they move away a little. In order to do this, there's this whole like expedition story about like 2 different groups to go and do this measurement during a solar eclipse, and they had to be down in the southern hemisphere. Big, whole long story that goes along with it. In the end, this is the sort of picture that we end up with, like our result from doing this experiment, where the yellow dots are this like group of stars, and where they normally would be, how we would see them, how they are relative to each other. But when you go and try to look at them when they're close to the sun, or when their light is passing close to the sun, they seem to move away, right? Because their light gets deflected into us, and if we look back, and it seems like it's coming from a little bit off to the side. And you see like the closest dot in there is deflected the most. The next closest dot still deflected a little bit, and less. So this had not really been noticed before, but Einstein, using his theory, predicted that you would see this. And this is exactly what we did see. I think this was actually sort of the confirmation that probably made Einstein into like an international celebrity at the time. But there are other tests we could do too. This one also with light passing near the sun, but this time with radio waves. So we keep doing tests, and we've done many different tests of general relativity over the years. The one that the book mentions like this is about one of the landers, I think on Mars, sending radio signals back to Earth. But right when Mars was like just at the edge of the sun relative to Earth, so that signal passes near the sun. We also did that sort of same thing with one of our space probes, Cassini. So basically you send a radio signal when Cassini is like just lined up almost at the edge of the sun and seeing Earth just at the other side, and you send a radio signal straight towards the Earth, it ends up getting delayed. It takes a little bit longer to get to the Earth than you would expect if space was just flat, if the light just continued to go straight. It doesn't go straight because space is curved, and so the light bends a little bit and takes a little bit longer of a path before it makes it to Earth. And that delay, the amount of the delay, is exactly what general relativity predicts. This image is sort of another way of viewing, like, I don't know, overlap of pictures of like the sun and the planets, and then the sort of grid, the blue purplish lines are indicating like the space-time, how it's sort of stretched. So around the sun, it stretches, pushed down. I should emphasize that this kind of effect, particularly to light, like mass creating effects on light, is something totally foreign to Newtonian gravity. Newton's theory of gravity doesn't make any predictions that mass would affect light at all, because gravity in Newton's view is just something that happens between objects that are massive, right? They're made up of matter. Light doesn't have any mass, so we would not expect any of this stuff to happen in Newtonian gravity. The last example we'll talk about has to do with GPS, shorthand for Global Positioning System. The image there is sort of the GPS satellite network. So the way that GPS works is using a sort of network of satellites that are constantly orbiting around the Earth, and there's like a couple of them that are seeing any given patch of the Earth at any time, and they're basically just beaming down the time on their clock. So just by getting signals from these clocks on these different satellites to a point on the globe, you can actually calculate where that position is on the globe. You don't need to know how that works. It's just to say that GPS doesn't work at all unless we're able to make very precise timing measurements. Measure durations of time very precisely, down to like millions and billions of a second. As I mentioned, space, time are interwoven in our new picture of space-time, and the Earth has its gravitational field. It may not be stretching space-time very much, but it does stretch it. And the closer you are to Earth, the stronger the gravitational field, so the more stretching there is. So if you're stretching space around the Earth, you're also stretching time around the Earth. And the closer you are to the Earth, the more of that time is stretched. That can be a confusing thing to think about. But the result of this stretching is that clocks on the surface of the Earth run a little bit slower than clocks that are orbiting in these satellites. So if the clocks are ticking slower on Earth, they're ticking a little bit faster up in the satellites. So these GPS clocks slowly get ahead, or would slowly get ahead of the clocks that are on Earth, which is very bad for GPS because GPS needs very precise times. And the effect here is actually not just from what we think of as general relativity. There's also another effect from what's known as special relativity, which has to do with objects moving very quickly. We're not really going to get into special relativity, I think, in this class. So I just wanted to point that out. But the overall effect of what you call a theory of relativity, meaning general relativity, special relativity together, is to tell us that the clocks on the GPS satellites are going to slowly get ahead of the clocks on Earth. And it's not very much, right? But again, relying on such precise timing, if we didn't account for that difference in timing, GPS positioning would get off by like 11 kilometers in one day, which would just be useless. Couldn't use GPS, right? We need it down to at least like, I don't know, like 10 meters, 50 feet or something. So I said, like, it needs very precise timing. The differences that add up to this like 11 kilometer difference in a day is only 45 millionths of a second, or 45 microsecond difference that adds up over the span of a day between the GPS satellite and a clock here on the surface of the Earth. So it's not that much, but the effect is quite large. If we didn't account for it, GPS would be useless. If we do account for it, GPS works just great. So there's another nice confirmation of Einstein's theory of relativity. That is about it for part one of this lecture. Like I said, pretty much just talking about space-time for a while, theory of relativity, general relativity in particular, and then in the second part, in the next lecture, actually talk about black holes, right? The collapse of very massive stars, and how general relativity predicts some strange things, but now we seem to be spotting them, so general relativity is checked off again. Cool. I will see you later.